Well, yeah, probably something like that.
Yeah,
Huh?
will work for
No, that's not the whole thing. Alrighty, so 4A. These are our application problems here. Solving problems with trigonometry. We want to solve problems involving right triangles and solve problems involving simple harmonic motion, but that's going to be Monday. We've got quite a bit to get through before we can get to simple harmonic motion. So definitions, in case we've forgotten from geometry. Angles of elevation, the angle through which the eye moves up from the horizontal to look at something above. You're standing there, you hear the sound of a helicopter, and you look up. That's going to be your angle of elevation from straight ahead on up. Angle of depression, the angle through which the eye moves down from horizontal to look at something below. You're walking along, and out of the corner of your eye, you see that penny. You remember, see a penny, pick it up, and all day you'll have good luck. And your sight is here, and now it's down here. So that's your angle of depression. And if we have that horizontal relationship looking straight out and the ground is flat, the angle of depression and the angle of elevation will actually be the same. And that should be, if we can remember way back from geometry, something that's obvious from that. Do you remember the name of those angles? They are congruent. Special name for the angle here. Alternate interior angles. Yeah, so when you have two parallel lines, the alternate interior angles are going to be congruent to each other. So the angle of elevation equals the angle of depression. Been too long, huh? Geometry is just a blip on your radar now. Using angle of depression, I'm going to start off very basic, stuff that you did in geometry. The angle of depression of a buoy from the top of the, I'm going to go with Barnegat Bay Lighthouse, 130 feet above the surface of the water is 6 degrees. Ooh, a picture. Love pictures. They're very, very, very helpful. Find the distance x from the base of the lighthouse to the buoy. And they already have everything nice and labeled for us right there. But what we have to realize is what we just talked about, which is that the angle of depression here and the angle of elevation will be congruent to each other. So we can actually put this little 6 degrees down here for theta. And notice it's in degrees. So with our calculators, we're going to want to double check. Do we have everything in degree mode? Make sure that's all set. Otherwise, our answers are just going to be bizarre. We're using radians throughout all this. So the next thing is good old SOHCAHTOA. And that's what we use here. We have a 130, and we need x. We have 6 degrees. We just need to figure out from that 6 degree angle which sides we're talking about and which trig function we use. So 6 degrees, this is opposite. This is adjacent. Which trig function just uses opposite and adjacent? Tangent. So the tangent of 6 degrees equals 130 over x. And remember, the tangent of 6 degrees, it's just a number. It looks fancy because it's tangent of 6 degrees, but it's a number that's in your calculator. So what we want to do is show the algebra that would give us a perfect answer. We don't want to start punching things in right now and manipulating. We want to get what we're trying to solve for out of the denominator, and that's because you can't leave what you're solving for in the denominator. So we would multiply both sides by x, and those would cancel. And then to get x by itself, we would just divide by the tangent of 6 degrees. And now it's calculator time. But notice the algebra is perfect up to that point. The answer, if they said leave your answer exact, we would have to leave it right there because that's a perfect exact answer. But bless you, they want us to figure out, find the distance x from the base. So we'll do that to 3 decimal places. We've got 130 divided by the tangent of 6 degrees. 1,236.867 feet. And, you know, think, well, do I need to convert that? Well, no, because they knew this was going to be kind of long. You know, if they do say find it in miles, we know there's 5,280 feet in a mile, and we convert that. But didn't say anything about that, we leave it as is. Now it gets a little harder. You know that because you look at the picture and you go, oh my gosh, we got a few triangles going on here. Let's see. From the top of the 100-foot tall Altgeld Hall, a man observes a car. So he's up here somewhere. Here he is. Observes a car moving toward the building. If the angle of depression of the car changes from 22 degrees to 46 degrees during the period of observation, how far does the car travel? So what we're trying to find is right here. But we're going to have to do that in a rather indirect way. So they have already told us, hey, this was 22 degrees. We put that in the triangle for you right there. We don't know this either. Well, we got to set up some tricks so we can figure out what we do know and what we want to find. There is a little triangle right here that we could set up with a little B right there. It just happens to be tangent again because we have opposite and adjacent. So the tangent of 46 degrees equals 100 over D. Wait a minute. That means we can find D. Multiply both sides by D. And divide by the tangent of 46 degrees. But I'm not punching that in. Neither are you. Because if we do that, we're going to have a wrong here. We weren't trying to find D. We're trying to find X. So what we want is all the algebra that we can punch in at one time to get X as accurate as possible. So I go back and I think, okay, now I'm taking this stuff off. I have to do something with this 22 and I have to use right angle trig. I have to use that triangle. I don't have a choice. So I know this angle is 22 and this is opposite, and I know this is the stuff I'm trying to find, that it's still tangent. So the tangent of 22 degrees equals 100 over X plus D. We need that entire side. Well, I'm going to get my variables where I can get at them. I've got to multiply both sides by X plus D. I don't want to distribute them if I don't have to, and I can move the tangent of 22 over the other side just by dividing. Really close to getting X. I just have to subtract D. Don't we know what D is? So we make one big equation out of this by saying, well, X equals our 100 over the tangent of 22 degrees minus, bless you, substitute what we know D is. Now you have that perfect answer right before you punch it in. You just have to punch it in carefully. We've got some fractions going here. So we should probably use a couple of sets of parentheses before we make that approximation. But we do have a perfect answer sitting there right now. So parentheses, 100 divided by the tangent of 22, parentheses, parentheses, and subtract parentheses, 100 divided by the tangent of 46 degrees, parentheses, parentheses. 150.940 feet. So definitely, I mean, the first reason that we use trigonometry for things is indirect measurement. But this one, definitely indirect. We had to go a couple roundabout ways to get what we needed because we had two unknowns that we were working with. All right. This looks very similar, except the placement of the the variables. Got a large helium-filled penguin. It's moored at the beginning of a parade route awaiting the start of the parade. Moored just means like a boat is moored at the dock. It's tied up and tied down. 2 cables attached to the underside of the penguin, and they make angles of 40 degrees and 48 degrees with the ground. They're in the same plane as a perpendicular line from the penguin to the ground. Boom. Same plane means we've got a 2-dimensional triangle here. And if the cables are attached to the ground 10 feet from each other, so this we know, how high above the ground is the penguin? Oh, last time at least they were on the same axis. This is going to be a little bit more complicated. So, it's a right triangle. We're going to use right triangle trade. It's what we do. And we'll have unknowns, and we'll have to think about what we're trying to find and how we want to set it up. So with the smaller triangle on the inside, let me just make that one red here. Even though they're both variables, we're still talking opposite and adjacent. So the tangent of 48 degrees equals h over x. So that's the setup for the smaller triangle. I'll go after this one in the blue. And I realize, well, it's still going to be, I need this side involved and this side involved. So the tangent of 40 degrees equals h over 10 plus x. Now we have both an h and an x in both of these. So it's a matter of deciding how we want to go after it, because there are actually 2 ways that you can, well, 2 basic ways you can solve this problem. We could either get h by itself or we could get x by itself. So one of the considerations might be to go up here and say, well, what were we trying to find? We were trying to find the height. So if I get x equals blah, 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 then I'll still have h's in my formula. And that'll give me the height right away. Some people would say it's easier just to get x by itself first, and then I'll go back and substitute that in. So I'm going to leave it up to you which way to solve this one.
For h.
For h? Okay, so let's get the x's alone so we can solve for h right away. So the red one up there, we have x tangent of 48 degrees equals h, and we would have to divide by the tangent of 48 degrees. So far so good. Now in the blue one, 10 plus x times the tangent of 40 degrees equals h. We divide by the tangent of 40 degrees. And we would subtract 10 from both sides. In the drawing, is there just one x? Well, then it has to equal itself. It has to. They have to be the same. They're the same x in both of these. So our red has to equal our blue. And now we see why a lot of people would have gone after fractions. If you don't like fractions, this one has fractions. The other one you wouldn't necessarily be dealing with fractions the whole way through the problem. But again, both of them will be right as long as we do this correctly. Do you remember what we do when we don't want to work with fractions? How do we get rid of fractions? That's if we have something that is already being multiplied by a fraction. This is an equation involving fractions, right? The LCD. Ick. The LCDs.
Pre-cal fun, right?
Yeah, it is fun.
what's our LCE?
Both of those. That's our LCD. So what we're gonna do, and I'm gonna spread this out a little bit so we can see it, is we're gonna have to multiply by both of those tangents. Because that's our LCD. So all the way across the top, we're going to multiply everything by both the tangent of 48 degrees and the tangent of 40 degrees. Which, kind of good news, you can see the canceling that's going to take place as we go through there. It'll get rid of them for us. And remember that even though it looks nasty, these are numbers that our calculator is holding for us. First fraction, tangent of 48, and cancel out. First blue fraction over here, tangent of 40, going to cancel out. Unfortunately, nothing gone out of this. Still just algebra. It looks really nasty, but it's still just algebra. What are we trying to solve for? H. H has to be on the same side in order for us to solve for it. So how are we going to move over H tan 48? Subtract it. Yeah, remember, it's tangent of 48 is just a number. That's all it is. So we'll have H tan 40 degrees minus H tan 48 degrees equals negative 10 times the tangent of 48 degrees times the tangent of 40 degrees. On no time do we grab a calculator and punch this in because the algebra has to be perfect up to your answer. Oh boy. How are we going to separate H from tan of 40 and tan of 48? What's factoring? Take it out. You know, it's like division. Division is factoring. We're pulling the H out of both of these. We're getting close. What do we do to get H all alone? Yeah, divide by that big monster. There is our perfect answer. Again, big set of parentheses for the numerator, big set of parentheses for the denominator, so the calculator knows do all this first, then divide. Whew. Okay, calculator, hang in there. Make sure you finish off your parentheses after you punch in tangent 48. You're going to get the same thing. Work very carefully. With trigonometry, you forget a set of parentheses after 40, you're in trouble. You know, you have to finish off those parentheses. So 34.323. What was this in feet? Yep. Geometry memory is coming back as we go through some of this stuff. Good, good. A little bit of it. All right, we found the penguin's height. 34.32 feet. Each one of these little tiles is 1 foot. It's a pretty big thing. That's a pretty good size thing. Looks complicated. Navigation. Using trigonometry and navigation, a U.S. Coast Guard patrol boat leaves Port Cleveland and averages 35 knots, nautical miles per hour, traveling for 2 hours on a course of 53 degrees. Okay, 53 degrees. Remember from true north. When you talk about bearing, it's always from true north. So there's the 53. Traveling for 2 hours on that course of 53 degrees. And then 3 hours on a course of 143 degrees. What is the boat's bearing and distance from Port Cleveland, which means from there to here? What are we talking about from that point? There's a lot going on in that picture. A lot going on. I don't like that. There's too much. So here's what I'm going to do. I'm going to go back to this. There's a big right triangle in this. I need to know that. And focus on the fact that I'm going to need this bearing right here. Because I know this is 53. If I just add this little angle, then I'm talking about true north. So I need this. Well, in order to find that stuff, I'm going to need a side or two. Well, I need that. So I have to figure out how far it is from A to B, because they told me about distance there, and they told me about speed and all that good stuff. And then same thing for BC, and then I could just use an inverse trig function. So let's see, they said 35 knots per hour for 2 hours. 35 knots per hour, that sounds like a rate. 2 hours, that sounds like a time. Do we have a formula that uses rate and time to give us distance? Distance equals rate times time. That's what we're going to have to use. It's as basic as that. So this first stretch, 35 knots for 2 hours. I'll put a little d(1) for first distance here, or we could even just put AB. So that's going to be 70 nautical miles per hour, or knots. All right, going to add that to my picture. Not enough for an inverse trig function. I need the ratio of 2 sides. You see, it said this is for 2 hours and then 3 hours. Did it say they changed speed? Anywhere in there did it say suddenly they're going faster or slower? Oh, good. We can still use the 35. Bless you. $35 times 3? Again? Thought I heard you wrong. Yeah, 105. 105 knots, and we could again label that BC. Can we figure out this distance now? How could we get that? Yeah, because they didn't just want to know the bearing, they also wanted to know the distance. Well, while we're working with the sides, we might as well continue working with the sides. And say 70 squared plus 105 squared equals, oh, let's put AC squared, so we're using the right geometry notation there. So 70 squared plus 105 squared, we're going to have 15,925 equals AC squared. Square root. Of 15,925. 126.194 knots. And again, that's as perfect the answer we're going to get for that distance. We had really nice numbers to use for the side lengths there, and they wanted to know the distance, so there's the new distance. One last thing is figuring out that bearing, and we need this angle right here. Which trig function should we use? Figure labels for those two sides. Kind of weird how everything we're doing today is tangent, isn't it? Yeah, we're going to use tangent again. This is opposite, and this is adjacent. So the tangent of our little theta is going to be 105 over 70. Okay, that's not a number between -1 and 1. Does it have to be? Not for tangent. For cosine and sine, yes, but not for tangent. Well, how am I supposed to get the angle? Those of you that are punching in, what are you punching in? I'm not punching in. I'm going to pretend I'm not punching in. What are you doing?
Inverse of them, and then I'm giving off 3 of them to double check.
Oh, not a bad plan. Yeah, it doesn't hurt to double check. Make sure they add up to 90. Well, we'll have to go 310 degrees. But that's not our bearing, because that was a piece we needed to tell them bearing. This is right here. But bearing is from true north. So the bearing means we're going to have to add that 53 to this nice little angle that we just had to get the bearing. So our bearing is what?
Degrees.
Thank you. And we don't have to say, we know it's from due north. Bearing, when you're talking about nautical stuff, always means from due north. So if we just say the bearing is 109.310 degrees, do we need the little bubble for degrees? Absolutely, we know we do. Because if there's nothing there, it's radians. And we aren't talking about radians today. We're talking about real world navigation. Well, that's as far as I thought I would get. So this is a good place to cut off. Give me your 43210. How do you feel about the word problems we did today? Yeah, they're still word problems, right? The penguin one? Yeah. Like I said, there's 2 ways to do the penguin one. Neither one of them is fantastic, but you go with what you got. Always draw a picture. I mean, you learned that in geometry. Always draw a picture. Well, apparently those must be simple harmonic motion. Peek and make sure.